All right, good evening and welcome to lecture 9 for MT225. Lecture 9 here, we're just about a third of the way through the class. We're getting moving on pretty quick here. Um, Tonight we're going to practice a little bit more on the stuff we worked on Monday night. A lot came at you Monday night, so I'm not surprised if perhaps things still seem a little bit jumbled there. But we'll work through some examples, give you a little bit more of a formal idea of how these supports work, so that we can get a good free body diagram. Once we've got our free body diagrams, it's the same process over and over again. In fact, because it is the same process over and over again in solving both concurrent and non-concurrent problems, I've written up a little procedure for both of those. You can find that on the website under the handouts section. If you go to the handout section, you'll find two PDFs, one labeled solution procedure concurrent and solution procedure non-concurrent. Essentially, it's the steps that we follow every single time we do one of these problems. So maybe useful to have next to you to make sure you're following the right steps. Also, not a bad thing to keep in mind for our upcoming exam. 2 weeks from tonight, we'll be having our first exam, covering everything from the beginning of the course. And the last new material for that exam will be next Monday night. But the For that exam, you will get to bring into the exam with you a uh, let's see what I use, 4x6 card, 4 inches by 6 inches, I think is what I specified. You can put anything you want on those cards, including sample problems, procedures. Don't worry about unit conversion factors. I'll give you those if you need them. But anything that you think might be helpful to you during the exam. So there's a little crib sheet you can make up. I'll remind you of that next week. So let's get going here. So homework 3 is due tonight, and I will open up the floor for questions on that in a moment. Quiz 2 was returned back to you on over the was yesterday. I returned it yesterday by email. If you didn't get one, get email on that, and you submitted a quiz. Make sure you talk to me. Make sure we figure out what happened there. If you didn't submit a quiz, I didn't return anything to you. So bear that in mind. And then homework 4 has been posted. That is due next Wednesday. We will have our third quiz next Monday. Same procedure. I'll post it sometime Sunday afternoon, and it'll be due before the end of the day Monday. And exam 1, there's our documentation of exam 1 on March 17th. All right. Anyone have any homework questions?
Do you think we could go over question number 4?
I think we can. So let's go over question number 4. Question number 4 is it's a good one because it looks kind of simple when you start out, and then you start getting into the math on it, and it ends up looking a lot more complex than it first did. I gave kind of a skeleton setup of the problem last week. On Monday night, I went through basically the free body diagram, and so we'll kind of pick it up there and work through the equations. But if you can solve problem 4, and you can work through the math on that, you can really handle pretty much any problem that I'd ever give you in this kind of class. It's about the highest level of mathematical sophistication. I'll also show you an alternate way to solve the problem that ends up being much easier than what you might have done so far. So let's take a look at it. Let's see here. All right, so problem 4, we had that box on an inclined plane. So we have this inclined plane. We have an angle of 30 degrees. We have some box, and I believe that weighs 20 pounds, tied up to a rope. And the first thing that I asked you to do last week, or on Monday when we looked at this, was to first make sure that you believe that this is in equilibrium. And this is in equilibrium. It has a chance of being in equilibrium. There's a tension on this rope that will hold that box in place. They get all the numbers right here: 30 and 30 degrees, 20 pounds. We good there? Is that the right? Well, let me verify with my homework sheet. There it is. Yep, 20-pound box, 30 degrees. All right. So we did the free body diagram, and we found that when we have something sitting on a surface, there is a reaction force. Reaction forces are generated by surfaces and other supporting mechanisms whenever a load is imposed on them. So this surface is generating a reaction force that pushes the box perpendicular to the surface. We call that the normal force. So in our free body diagram, remember in a free body diagram, we are putting a little bubble around our body of interest, and anything that touches or crosses that bubble has to be represented in the free body diagram. So here's our weight. Gravity is the only thing that doesn't automatically show up. So we have to put that in. There's a gravitational force of 20 pounds because it's a 20-pound box. There was a force up the incline due to the tension in the wire. So we'll label that T. Now that is lined up parallel to the surface. So it's at a 30-degree angle to horizontal. The normal force is the force that's perpendicular to the surface. That's the reaction force from the surface. Where that surface and the object are touching, that's where that force exists. So that has to be in there too. If you don't know to put that in, you'll end up with a set of forces that can't be in equilibrium. If we know it's in equilibrium and our forces can't be in equilibrium from our free body diagram, we know we missed something. And that's our normal force there. And that, because it is perpendicular to the surface, it's 30 degrees away from vertical. And the question is asking, how much tension do we have in the rope? So that's all we really want, is the tension in the rope. Now, this is a concurrent force system, and with a concurrent force system, we can handle up to two unknowns, and we do have two unknowns here. We've got our unknown tension and our unknown normal force. And sometimes this happens in problems. You really want one thing, but to get that thing, you might have to solve for something else in between. That happens sometimes. You can't always come up with a solution that gives you only what you want and nothing else. So in this case, we'd have to figure out the normal force along with this, because our equations of equilibrium are going to be tangled together. We're going to have a set of simultaneous equations there. Not the worst possible set of simultaneous equations, but definitely a set that definitely a little harder to solve than what we've had to do with most of the problems, with all the other problems on the homework. So we've drawn our free body diagram, and the next step in the process is to select a coordinate system. And the tendency is to go with the traditional coordinate system, where horizontal is X and to the right is positive and vertical is Y and up. That choice of coordinate system makes the representation of gravity easy, because gravity is all along the Y component. The tension and the normal force are at angles here. So there's going to be an X and a Y component for the tension. There's going to be an X and a Y component for the normal force. So let's break these up. We've got, we'll label these here. We'll call that vector 1. We'll call that vector 2. And maybe this one vector 3. So we'll go over here. Vector 1, that's our weight. It has an X and Y component, but the X component's 0. No component to the X direction, all Y. Vector 2, we don't know what the tension is, but we do know the angle. And when that's the case, we use sine and cosine, because sine and cosine of 30 is they're just numbers. So they're just going to be coefficients on this one unknown t. We don't want to get into a situation where we're multiplying two unknowns together. That's why when we have both an unknown magnitude and unknown direction, we do the components. We do t1x and tx and ty. But when you do have one of the pieces, remember, a vector is a two piece of information object. It needs two pieces of information to describe it. When you've got one of those two, it's always going to be easiest to work it out in components. So we need the x and y components of the tension. The x components are horizontal piece. That's the adjacent side. So adjacent goes with cosine. So this would be t cosine of 30 degrees. The y components, the opposite side. Opposite goes with sine. So t sine 30 degrees. And then we've got vector 3. And vector 3, we've got x and y components. The y component here is the adjacent side. If we use the angle that we're given here, which is 30 degrees to vertical, cosine will give us the y component. So we've got n cosine 30 for our y component. And then we'll have our x component being the opposite side. Opposite goes with sine. So we've got n sine of 30. Now your setup might look different. If you decided you really didn't want to deal with an angle to vertical and instead wanted to figure out the angle to horizontal, you certainly could do that. You'd figure out at 60 degrees and you'd have cosine and sine of 60 degrees here. That works. It's no big deal. The answers cannot depend on the way you break these vectors up. As long as you break them up the right way, that is using the right values for the angle. It doesn't matter if you use the vertical or the horizontal, you'll get the same numbers in the end. The answers also can't depend on our choice of coordinate system. Coordinate system is something we impose on the problem. Reality doesn't involve a coordinate system. It's a tool we use to make sense of it. So the answers, if they're physical, can't depend on what we choose for our coordinate system. It can affect how easy the math is or how hard the math is, since it's the coordinate system that generates these components. So we can put some numbers on this here by evaluating the cosine and sine of 30. Cosine of 30 is 0.86603. So we've got 0.86603 t there. And sine of 30 is half, 0.5. And then we've got similarly 0.5 n and 0.86603 t. So there we've got our vectors all broken up into components. We can now do our sum of forces and get our equations of equilibrium. So let's do our sum of forces. If we do our sum of forces in the x direction, from vector 1, I've got nothing. Vector 2, I've got 0.86603 t. But that is the x components to the left. Left is negative according to our coordinate system. And then for vector 3, I've got 0.5 n. That's to the right, since the normal force is up and to the right. The to the right part, 0.5 n, that's positive. Then we have our sum of forces in the y direction. In the y direction, we've got negative 20, since we've got 20 pounds pulling down. We've got 0.5 t, and that's up. So positive 0.5 t. And then we've got, for our normal force, our y components also up. So plus 0.86603. Oops, that should be n. So 0.86603 n. So there we've got our sums. To make these into our equations of equilibrium, we have to set them equal to 0. So I'm going to do that down here where I've got a little more space. So my x direction equation is negative 0.86603 t plus 0.5 n. That equals 0. And I've got negative 20 plus 0.5 t plus 0.86603 n equals 0. Definitely a set of simultaneous equations. Definitely something that we're going to need to untangle to solve. Any questions up to the equations?
I got a quick question.
Go ahead, Doug.
Does it matter if we use N? I mean, I got mine T1, T2.
No, it doesn't matter. I use the letters don't make any difference. It's just a name.
Right.
So if you can label them whatever you want. You call them Bob and Steve if you want to. It doesn't make any difference at all. I'm just using the traditional names, which is tension, T for tension, and N for normal force. But now, if you got the same equation, but you've got X or Y or T1, T2, it doesn't make any difference at all.
All right, thanks.
All right. So let's clean these up a little bit here and get them into more of a standard form. The standard form for an equation set like this would have the terms with symbols in them on one side and all the pure numbers on the other. So I really don't have to do anything to the first equation. I can just write it as 0.86603t plus 0.5 n equals 0. The second equation, I'd add 20 to both sides and get 0.5t plus 0.86603n equals 20. So there's our set of simultaneous equations. And like I promised you at the beginning of the semester, we don't typically see simultaneous equations come up in the nice simple 3x plus 2y equals 5 and 2x minus 3y equals negative 5. They don't come up with nice whole number coefficients that you can easily manipulate. In reality, the coefficients tend to be sines and cosines of angles, which is exactly what we saw in this problem. So we have a way to solve that. We can apply the same basic principles. We want to get the coefficients on one of these two unknowns to be the same size, but opposite signs. And I've already got built in here a sign difference with my tension. I've got a negative something t in the first equation and a positive something t in the other. If I can make both of those be 1, but one of them be negative 1 and the other one be positive 1, I can add the two equations together and it will eliminate the tension and leave me with just an equation for the normal force. Once I have the normal force, I can back solve and figure out the tension from one of the two equations. So that'll be our game plan here. Now, the easiest thing to do is to turn these coefficients into 1 by dividing out the coefficient. You can change an equation by multiplying or dividing every term by the same number. So every term gets multiplied or divided by the same number on both sides. So to make this 0.86603 go away, I'm going to divide by 0.86603. So I'm going to transform this equation by dividing by 0.86603. Now, when I divide the first term by that, I'm going to just get negative t, negative 1t. But 0.5 divided by 0.86603, I should probably go to my calculator for that, though I've got a sneaking suspicion I know what the number is. But we've got 0.5 and 0.86603 should give me Yep, 0.57735 rounded to 5 sig figs. So this is plus 0.57735 n. And that still equals 0 because if we divide the right-hand side 0 by 0.86603, we get the same number. Now, dividing through on the second equation, 0.86603 isn't going to work because that's going to make my coefficient of t ugly. So instead, I'm going to divide through by 0.5. So if I divide by 0.5 here, divide by 0.5 here, divide by 0.5 there, it'll change what the equation looks like, but it won't change what the equation says. So it won't change our values. Well, 0.5 divided by 0.5, that just gives me t. 0.86603 divided by 0.5 gives us 1.7321. So plus 1.7321 n, and 20 divided by 0.5 is 40. Now the coefficients for n, they look worse than they did before, but the coefficients in front of t look better. If I add these two equations together, I've got a minus t plus t. That will cancel out. I've got 1.7321 plus 0.57735. That gives me 2.3095. N. 0 plus 40 is 40. And if we divide both sides by 2.3095, we'll get our answer, for n anyway, of 17.320, and that's pounds. So what that tells us is that the floor here, whatever this is pushing up on the object with a force of 17.320 pounds. That could be important to know in some problems. It could be important to know, for example, if you're worried about perhaps this thing giving way. Maybe that force is too much in this area. If this material isn't capable of generating that kind of force, it's going to break, or at least it's going to deform. It's going to change shape. But in this problem, we don't care what that normal force is. What we care about is the tension. So we can go back up to, I'm going to take this equation, the x direction equation. We can plug in our n value and solve it for t. So we can do what we call back solving. We can go back to our original equations so we can solve for the missing piece. So we've got negative 0.86603 times our tension plus 0.5 times 17.320. That equals 0. There we are. Well, 0.5 times 17.320 is 8.6601. Right, let's see. I might have kept something in my calculator there, so let me stay true to continuing to round to 3 sig figs here. 320.5. Yeah, 8.6600. And that equals 0. To solve, I would probably add the negative 0.86603t to both sides. That'll give me 8.6600 equals negative 0.86603t. Then we can divide both sides. 0.86603, 0.86603. And if we divide that out, we get our tension value, and that is looks like it comes up to be to 5 sig figs. It would be 9.9997. But if we round down to some more reasonable value as our final answer, round down to 3 sig figs here, we'd have 10. So to 3 sig figs, our answer for our tension comes out to be 10.0 pounds. So the tension comes out to be 10 pounds. After all that math, 10 pounds. So half the weight. When we're on a 30-degree incline, we have half the weight. And there are all sorts of different ways to think about that. If you think about it in the context of a simple machine, simple machines have mechanical advantages, and with a 30-degree angle here, you have a mechanical advantage of 2. So you can lift something up the incline with half the force of directly lifting it. But that's all the math is, figuring out the simultaneous equations. Now, if you had down here decided to eliminate n instead of t, you would have gotten your value for t right away. But you don't have to. You could solve for n, solve for t, find the whole solution. But it should come out to be 10 pounds. Now, that's the hard way of doing it. There is actually an easier way here, and it's rare that this kind of situation comes up, but we have kind of an advantage here with the way that the unknown forces are angled. We can choose a slightly different coordinate system. And if we choose a slightly different coordinate system, we can simplify the unknown quantities versus our known force. But before I show you how to do that, does anyone have any questions on working through the simultaneous equations on that one? All right, so let's see here. So let me go to another page here and redraw, well, won't redraw it, but I will put a slightly different coordinate system into play. The coordinate system we picked up here, the traditional coordinate system, it made the representation of this weight vector simple, but it complexified the representation of these two. If you have a choice about it, you should always pick the coordinate system so that it simplifies at least one of your unknowns. That minimizes your chances of getting into a simultaneous equation situation. Physically, what it means to do is to pick a coordinate system that is more aligned with the physical nature of the problem. And if we look at the physical problem over here, a better coordinate system would be one that puts x down the ramp and puts y perpendicular to the ramp. We can do that. There's nothing saying x always has to be horizontal and y always has to be vertical. We can rotate it to any angle we want. And if we do that, we get a different set of equations because our vectors break up differently. Since our equations are based on how we take angles from our coordinate system, if we change how the coordinate system looks, we can get different angles and different equations. They all have to solve to the same thing. So this doesn't change the answer to the problem, but it changes the math that gets you to that answer. So let's redraw, or let's do the free body diagram, but with a different coordinate system, with a coordinate system where x is down the ramp and y is perpendicular to the ramp. In that case, our vectors will break up a little bit differently. We'll have our weight vector, which I'll come back to in a second. That one's going to be a little more complex. It's not going to be as easy as what it was before because it doesn't have the coordinate system lined up with it. But vector 2, our tension, that is now all x component because it's all along the surface. So my x component's just t. My y component, 0, because the tension has no component perpendicular to the surface. For vector 3, the normal force, that's all perpendicular to the surface. So it has no x component and all y component. So my y component is just n. So by rotating the coordinate system a little bit, we've simplified the representation of our unknown vectors. That'll make for simpler equations. Now we have made more complex our weight vector. Our weight vector is now going to have an x and a y component because that weight vector is pulling down here. There is a piece of it perpendicular and a piece of it parallel. A piece of it is along y and a piece of it's along x. So we'd have to figure that out. But once we get our numbers for that, we'll have simpler equations. So let's look at figuring out the weight vector. And it's a lot easier, I think, to see the weight vector if we draw out the full set of axes. So I don't usually draw out the full set of axes, but when things get tilted around like this, it's important to keep some perspective on it. Our weight vector is right there. That's our 20-pound force. So let me get that on the screen. There we go. That's our 20-pound force. And we have to make sure we're clear about what angle that is. That angle is going to be the same as this angle. If you picture the coordinate system that we first used, where x was horizontal and y was vertical, and we rotate that clockwise 30 degrees to line it up with the surface, to line it up so that the x axis is parallel to the surface. That means something that used to be straight down is now going to be 30 degrees off. So this angle right here is 30 degrees. And I find it's useful in a lot of situations when you have to rotate a coordinate system to picture what it looks like flat, and then imagine how that rotation would go so that you can figure out what the right angles are going to be. Because a common mistake would be to say, well, this angle is 30 degrees and flip your coordinates. So it's this angle here to vertical that is 30 degrees. So we have, and in fact, if it makes more sense to you, you could always rotate it like that so that you can figure out what your y and your x pieces would be. But our y piece here is our adjacent side. Adjacent goes with cosine. So we'd have 20 cosine of 30. And then our x component, that's the opposite side. So that's 20 sine 30. So the weight gets a little more complex, but it's just numbers at that point. It's not symbols. And if we're going to put complexity somewhere, we may as well put it where there are numbers and not symbols. So let's do our sum of forces. Sum of forces in the x direction. Well, we've got 20 sine 30. That's our weight, and that's downhill. It's down the ramp. So that's positive. So we have 20 sine 30, which just happens to be 10. Sine of 30 is 0.5. Then we've got our tension. That's all uphill. Uphill here is negative. So we have 10 minus t. That's our x direction equation. Looks a heck of a lot nicer than it did in the previous problem, where we had 0.86603t plus 0.5n, but no weight. Let's do the y direction. Sum of forces in the y direction. We've got the y component of gravity, which is down, so that's negative, and that's 20 cosine 30, which will come out to be 17.321. Nothing from the tension force, but everything from the normal force plus n. This is an equilibrium, so the sums have to equal 0. Now we've got two equations that have been decoupled. These two equations have been separated from each other. By rotating the coordinate system to something more natural for that problem, we were able to separate the two equations. So now we don't need simultaneous equations to solve this. In fact, we don't even need to look at the y direction equation at all, because we don't care about what the normal force is in this problem. All we have to do is solve the x direction equation, and that hopefully the solution to that one jumps right off the page at you. The tension is 10 pounds. So by picking a different coordinate system, and the point of this problem is to illustrate first that no matter what way you solve it, you're going to get to the same answer in the end. So although the math might be a little bit harder one way or another, as long as you can hack the math, you can get the right answer. The other point here is that sometimes we can make choices about how we set up the problem that will simplify things in the long run. So it's worth looking at the problem a little bit and kind of thinking ahead and seeing what would be the most advantageous coordinate system to pick, or what would be the right point to reference when we're doing things like moments. Picking our pivot points is another place where we have a choice in the problem. Now, either solution's good. Some situations, a lot of situations, we can't do this. We won't get a simplification. We'll just get a different set of complex equations we'll have to solve. But it just so happens in this particular one, because our unknowns are perpendicular to each other, rotating the coordinate system to line that up simplifies things greatly. Questions on that one? Any other questions on the homework? All right, then let's proceed. So tonight we'll review equilibrium in non-concurrent force systems and remind you what the new equations of equilibrium look like when we're moving on to a non-concurrent system and moment comes into play. I'll give you a little bit of a more formal introduction to supports and reaction forces and how we can look at a system and determine how to represent the reaction forces. And then we'll do some more examples and you'll have some more practice. So last time we saw that in order for a system to be in equilibrium, we need two conditions. We can't just have one. For a non-concurrent system, for a concurrent force system, the ones we started out with, it was enough to say the sum of forces was 0. But that ignores rotations. In systems that can rotate, we have to also have the sum of moments equal to 0. And the vast majority of realistic systems out there have the ability to rotate. They are non-concurrent systems. So torques are present. And we need to have the sum of moments be 0. Now that gives us three equations, because although moments are vectors, they're restricted in our situation because we're in two dimensions. So there are only two possibilities, positive or negative, for moments. Forces, however, are two-dimensional. So we get two equations out of the forces, that the sum of forces in the x and the y direction are 0, but one equation from the moments, that the sum of moments about some point must equal 0. That gives us three equations. It also gives us the possibility of handling up to 3 unknowns. If we have more than 3 unknowns, we're in trouble. It basically tells us we've got to go measure something. We've got to go get some more information because we can't solve those equations. So we have enough information to solve for, at most, 3 unknowns. And we looked at moments last time. Moments are twisting forces. They're torques that a force exerts about a point. The arm is the distance between the pivot point, which is something we select. So once you pick a pivot point, measure all of your arms from that location. just like measuring from the datum in doing weight and balance. You make everything measured from the datum. Don't throw in a measurement from the nose wheel unless the nose wheel is a datum. So the arm is the distance between the pivot point and the point of application of the force. And how we calculate the moment is that we have to deal with the perpendicular component of force. In the past with moments, we've assumed that we had a 90-degree angle there, or we set things up so we had a 90-degree angle, leveling the airplane. But in reality, we can't always do that. So we have to deal with the fact that there will sometimes be an angle between the arm and the force. And we fix it by taking the perpendicular component. We figure out the perpendicular component times the length of the arm. So the equation is force perpendicular, times the arm. That's the moment. The parallel component does not create a moment. It just pulls on the hinges. And then we defined our sign convention. In general, positive moments are counterclockwise and negative moments are clockwise. It's opposite to what you've probably become used to in the A&P program, but this is by far the greater standard. This is what's used almost universally out there. A&P is the exception, not the rule. So counterclockwise moments are positive, clockwise moments are negative. And I'll remind us of that when we work on problems by drawing a coordinate system that shows the direction of positive moments. So let's look at supports here before we jump into another problem. And supports are important because they are usually, at least at first, what we're interested in figuring out in a structure. Think of it kind of like building a house. When you build a house, you've got to put in a foundation. The size and the shape of that foundation depend on what you intend to sit on it, what kind of load you expect to apply to it. In a house, all the structural forces, the weight of the house, the weight of the contents, the occupants, the roof, the snow loads on the roof, all of that eventually bears on the foundation. And if the foundation's got the wrong size, then structural failure starts to happen. So learning about what kind of forces we expect on our foundation, on our supports, is important to the overall design of a structure. And the problems we'll be working tonight and we'll be practicing on also next week form the foundation of all the problems that we'll be solving in our next third of the course when we look at trusses. The first step in solving a truss problem is solving for the reactions at the supports. So we've really got to get a good handle on supports and reaction forces. So when we create a free body diagram, like we did last week when we put the bubble around the beam, the things that are supporting the beam are replaced by representations of the forces they supply. Those are reaction forces. The action is placing load on the beam. The reaction is how the supports change to apply forces to the beam to keep it in equilibrium. We think of supports as reactive because the load can potentially change. In a realistic situation, the loads that are on a foundation change on a daily basis. Just look at what we've gone through, say, this week. I mean, we had a good bit of snow, then we had some thawing, we had some wind, we had all sorts of different forces applied onto the structures. That changes the load on the foundation, and the foundation has to change in response. So the foundation reacts to the loads that are on the structure at any given time. Different types of supports are out there. There are different ways of supporting a structure, and we'll see a few of these here. By far, the most common ones we use, we'll see relatively frequently, are what we call pinned supports and roller supports. Those tend to be part of every major structure in one way or another. And so those will be the ones we spend most of our time with, but there are plenty of others. And we can generally classify them based on how many unknowns there are about them. That is, how many dimensions are they? Are they described by just one number, by two numbers, or maybe even three numbers? So let's look at the one-dimensional reactions first. One-dimensional reactions only involve one unknown quantity. Think about things like cables, ropes, or chains. When we apply forces to cables, ropes, chains, wires, the angle is immediately clear. We know exactly what the angle is. It's whatever the angle is that the chain makes with whatever reference we're dealing with. If we pull on a chain at 45 degrees, that's the same as the direction of the force. What we don't know is how much tension we're using, but we do know the angle. So only one number comes out of a rope, a chain, a wire in a free body diagram, whatever tension is carried by it. So we get one reaction force, one unknown, along the cable. So the angle is well known. We have what's called a roller, and rollers are very, very common. And you can simulate a roller if you take a pen or something like that and put it on a table. If you push down on that pen, try to squish it between the table and your hand, the pen fights you. It resists. It doesn't want to get crushed. It pushes back against you. That's its reaction. If you try to push sideways, it really doesn't fight you. It just rolls. So there's no opposition. There's no way to react to a sideways load with a roller. Rollers always apply a force perpendicular to whatever surface they're sitting on. So if they're sitting on a flat surface, they react upward. They can also react downward. If you think of the roller as kind of being in a little track or something like that, it could resist being pulled up as well. But traditional rollers can't take a lifting force, but they can deal with a compressive force. So rollers give us one reaction perpendicular to the surface. And that's really true of any smooth surface. If you look at the surface like an icy surface, nice, smooth, icy surface, it's not going to oppose you if you try to go sideways. That's why you slide on it. But it will bear your weight. It will push up against you. The ice gets thick enough, it can support quite a bit. There are plenty of runways out there, for example, that pop up around this time of year to land airplanes on that are just made of ice. So smooth surfaces are essentially like rollers. They apply one reaction force perpendicular to the surface. Then we've got reaction forces, or we've got supports that give us reactions along multiple directions. The most common one that we'll deal with is what we call a pinned support. A pin is the same thing essentially as a hinge. If you think about a hinge on a door, that hinge is keeping you from pulling the door off the hinges perpendicular to the jamb or parallel to the jamb. It's fighting you in two directions, but it can't fight you if you try to rotate. If you try to open the door or close the door, it just rotates with you. As long as the hinge is working fine, it will allow moment to rotate it. A pinned support, a hinge support, a knife edge support contributes two unknowns. And we're going to see in problems, it's going to be easiest for us to represent those two unknowns as two components of the force generated by that reaction. So a horizontal and a vertical reaction force. Essentially, we don't know anything about the vector that the pinned support or the hinge support supplies. And when we don't know anything about the vector, we always just represent it as its components. So we get two reaction forces, and we split it up perpendicular and parallel to whatever coordinate system we happen to be using. Then there's the fixed support. Fixed supports, the easiest way to think of a fixed support is to think about taking a bucket of wet concrete and jamming a post into the middle of it, and then letting the concrete set. That's a fixed support. Fixed supports will fight you if you try to rotate that beam. So it'll fight you with respect to moment. If you try to pull the beam out, it's going to fight you. If you try to push the beam side to side, it'll fight you. A fixed support gives us three reaction forces. One reaction moment and two reaction forces. We don't deal too much with fixed supports in this portion of the class, but we'll take a look at them when we get into beams toward the strength of materials portion. So let's set up and solve kind of a basic problem here, really common problem, one that you should really get the solution down to. So good place to tag in the video here and go back and review if necessary, because this will be the first step in solving lots of problems later on. So let's take a look at problem that looks something like this. So let's take a beam, kind of similar to what we worked on Monday night, but this time we will give it a little bit more of a support. Last time we put a roller support at one end. Now the roller support only produces a force perpendicular to the surface. And I put another roller at the other end. And that's fine as long as I don't have any side forces. If I have sideways forces, putting two rollers here isn't going to be great. It's going to roll. It's going to be dynamic. We want it to be stationary. So we're going to put a pinned support at this end. And the symbol we use for a pinned support is a triangle. The triangle is a pinned support. And the pinned support prevents this thing from rolling side to side. It also prevents it from being pulled up or pushed down. So those are the two reactions we get out of it. Roller only reacts in one direction, perpendicular to the surface. So we'll imagine this whole thing is sitting on some surface somewhere. So there's our beam. Let's go ahead and load up the beam. So I'm going to put, let's see, we'll do a 10 kip force here. Remember, kips are thousands of pounds. And then I'm going to put, let's say over here, we'll put it right at the middle of the beam. We'll put something pulling up with 5 kips of force at 60 degrees to horizontal. And we'll put some geometry on the beam. Make this distance 2 feet. Make that 4 feet. And we'll make the entire length of the beam 12 feet long. Now, our goal in this problem is to look at the foundations. We want to know at points A and B, at those supports, what forces are those supports applying to the beam to keep it in equilibrium? So while we're going to be using the beam as our body, we're really trying to figure out what are the forces that the foundation, the supports, are applying to the body to keep it in equilibrium. So the question here would be, find the reactions at the supports, or find the reaction forces at A and B. That would be the problem we're trying to solve here. So let's go ahead and set it up. So in a non-concurrent force system, we start out the same way we start out a concurrent force system. We draw a free body diagram. So I'm going to draw my bubble around the beam. Now we're going to assume this beam is weightless, so we don't have to worry about how much weight the beam is supplying to the supports. We're only looking at what the results are because of the applied forces. Now anything that touches the beam or crosses that bubble needs to be in our free body diagram. So our free body diagram we'll draw down below here. We'll start with the easy part here, the applied forces. We've got 10 kips there. And we've got our 5 kips off at 60 degrees. But now we need to represent the supports. Rollers push perpendicular to the surface. So since the surface is horizontal here, the force that roller B is going to apply to the beam is straight up. So we're going to have a reaction here at B. And we can label that RB. I usually like to label it RBY since I know it's in the Y direction. And we'll use our traditional coordinate system here. X to the right is positive, horizontal to the right is positive, vertical up is positive, and counterclockwise moments will be positive. Let me get to the pinned supported A. Pinned supports generate two reaction forces. And I usually like to represent those reaction forces just as horizontal and vertical. And when in doubt, always best to assume things are in the positive direction. Unless you have a really strong indication that it should be in the opposite direction, it should be negative, or to the left or down, draw it to the right and up. So I'm going to do that here. I don't know exactly what force to expect here, but I'm going to replace my pinned support with two reactions. One is a reaction at A in the Y direction, which we'll call RAY. And then we have a reaction at A in the X direction, RAX. Now I have made an assumption here. In fact, I've made three assumptions because it's not always clear from the forces. This is a reasonably simple problem. As they get more complex, it may not be clear what the right directions are for these. We make assumptions, and then the math will tell us if our assumptions were correct. If our assumptions were correct, our answers will come out positive. Positive is confirmation that your arrows are drawn the right way. If you get a negative answer, it means your arrow should have been drawn the opposite way for that answer. So we'll let the math tell us whether our assumption is right or wrong. You may be able to predict it in the simpler problems, but in the more complex problems, it won't be as easy. So make sure you check those assumptions and watch your signs carefully. So there's our free body diagram. Any questions on the setup for the free body diagram? All right, so let's go ahead and set up our equations of equilibrium. So our sum of forces in the x direction, sum of forces in the y direction, and sum of moments about a point. So let's take our x direction forces, and we're starting to get a lot of forces in here. It's going to be a good idea to make sure you go in some sort of pattern or double check and make sure you've caught everything. One of the common errors I find people make with this is they'll lose a force. And if you forget one of the forces, you're going to get a different answer than you would if that force was included. So sum of forces in the x direction. So I'm just going to march left to right and pick up any x components that I've got. So I've got RAX, and I've assumed that to the right, so that'll go in positive. RAY doesn't have an x component because it's straight up. 10 kips doesn't have an x component. This 5 kip force does have an x component. That 5 kip force has a horizontal x component. That x component is going to be to the right, and it's adjacent to that 60-degree angle. So it's to the right, so it's positive. It's adjacent, so it goes with cosine. It's got to be 5 cosine 60. And we'll work the numbers down as we solve the equations. And then RBY, no x component there. So that's all I've got for my x components. If I take my sum of forces in the y direction, I've got nothing from RAX. I've got positive RAY. I've got 10 kips pushing down, so that's negative 10. I'm going to have a piece of this 5 kips pulling up. That would be the vertical piece here. That's the opposite side. So that's got to be my sine 60. If 5 cosine 60 shows up in one equation, it's a pretty good bet that 5 sine 60 is going to show up in the other. Hopefully you've picked up on that little pattern there. But that's up, so it's going to be positive 5 sine 60 degrees. And then we've got RBY, and RBY is up. So it goes in positive. So there we've got our sums in the X and the Y directions. We need our sum of moments. And our sum of moments is going to be easiest to pick a pivot point first. And almost always in these types of problems, the pivot point's going to be best if it's at one of your supports. Now, that doesn't necessarily mean it's always going to be at the end of the beam. These supports can be anywhere. They don't have to be right at the ends. These supports can be in the middle. They could be, one could be inset from the end. But if you pick your pivot point to be the location of one of those supports, then it's likely going to work out and make the problem a little easier to solve. If you pick the pivot point somewhere in between, you run the risk of having multiple unknowns show up in your moment equation. And I can say this with, I believe, without contradiction in this class. If you set up, I think every single problem you solve in this class, if you get more than one unknown in your moment equation, you didn't pick a good point. There's in every single problem, I think it's a consequence of us being in two dimensions here, that there's always going to be a pivot point that you can pick that will knock out everything except one unknown. So if you end up with two unknowns in your moment equation, you ever end up with a moment equation you can't immediately solve, go back and try a different pivot point. So let's pick a pivot point. And I'm going to pick point A as my pivot point. So I'm going to take the sum of moments about point A. So that means going through and only including forces that have moments. So what I like to do before I start writing anything down is I like to look at the forces and decide which forces are going to have moments. Well, RAX and RAY, those guys are out. No moments from them because they're pushing on the pivot point. They're pushing on the hinge. The arm is 0. The 10 kip force, that's going to have a moment because it's got some arm distance between the pivot point and the point of application. The 5 kip force, a piece of this will have a moment. The horizontal piece won't, but the vertical piece will. The perpendicular component is what creates the moment. And then we've got RBY. RBY is definitely going to have a moment in there. Now, if you go back and count the check marks here, I've got 3 of them. That means I need to have 3 terms in my moment equation. I will have accounted for every force that has a moment. So let's figure out our arms here. We've got this 10 kip force. It's 2 feet away from the pivot point. So our arm is 2 feet. Our force is 10 kips. We multiply the arm and the force to get the moment. So that'd be 20 kip feet. So that'd be our first entry here, 20 kip feet, foot kips, whatever you want to say. Then we have to figure out the direction. And especially when there are a lot of forces involved, it might not be as easy to figure out the direction if you try to take into account all the forces at once. Just look at the force you're interested in. Turn all the other forces off. Imagine pinning this beam to the wall through your pivot point and pushing in the direction of the force you're looking at. What direction is this thing going to rotate in? Well, it's going to rotate clockwise. And according to our coordinate system, clockwise rotations are negative. They're against the arrow. So we get negative 20. We can go to our next one here. The 5 kip vertical force, that was our y component, 5 sine 60. That is 6 feet away. So we'll have 6 times 5 sine 60. And we'll work out the numbers when we work out the equations. But 6 is the arm. 5 sine 60 is the force. Now that one's pulling up. If we turn all the other forces off and we pin here, pull up there, counterclockwise rotation. And counterclockwise rotations are positive. So we have positive 6 times 5 sine 60. And then finally, we've got RBY. Now, RBY, according to our drawing, is 12 feet away. Don't forget that. Most common error I see people make is they say, okay, well, plus RBY. And then they solve and they get unreasonably huge values for their reaction force. Moments are going into this equation, and moments are arm times force. So you've got 12 feet times RBY, so it's 12 RBY. And if we push up there, that would be a counterclockwise rotation. Counterclockwise moments are positive. So there's our moment equation. 3 terms, each one arm times force, 2 times 10, 6 times 560, 12 RBY. So that's our moment equation. So let's get our equations of equilibrium by setting the sums equal to 0. So there we've got our 3 equations of equilibrium. So let's solve these here. The simplest one to solve is the x direction equation. We've got RAX plus 5 cosine 60. So if we go over to the calculator to crunch the numbers down a little bit, we have 5 cosine 60. Well, that just happens to be 2.5. So this piece right here, that's 2.5. So we've got RAX plus 2.5 equals 0. If we subtract 2.5 from both sides, RAX equals negative 2.5 kips. All our forces are in kips in this problem. Well, let's look at that answer for a second here. Came out negative. If we set up everything exactly right, if we made all the right assumptions, we'd only ever get positive answers. We got a negative answer here. And that means we assumed RAX's direction incorrectly. I assumed that the pinned support would have to push the beam to the right, while the reality is it has to pull it to the left. And that kind of makes sense if you look at the applied force here. The only applied force with a sideways load to it is this 5 kip force at 60 degrees. It's pulling to the right. To be in equilibrium, if there's something pulling to the right, there better be something else pulling to the left to cancel it out. So we got this negative answer. That just means that the direction was wrong here. So at the end of the problem, we'll fix up the directions. We'll either draw a new drawing showing the directions, or we'll write up the answers and include the directions in there, which is a perfectly fine way to go. So I'll show you how to do that here. But that's what RAX gets us, negative 2.5 kips. Now, if RAX happened to show up in one of these two equations, you'd have to use it as negative. This is the numerical value of this symbol. So any place else that symbol shows up, it shows up with that same numerical value. You can't go back in the middle of the problem and just flip the arrow, because that would change the equations. You've already generated these equations based on your assumptions up here. So you can't go back and fix things until the end of the problem. You got to work with the assumptions you set. Now in the y direction equation, we really can't do anything with that just yet. I mean, we can crunch down what 5 sine 60 is. That'll give us 4.3301. But we really can't do anything with that equation because we've got too many unknowns. But we can work with our moment equation. With the moment equation, we've just got some numbers and RBY, 12 RBY. So let's get that numbers set up here first. So 6 times 5 cosine or sine of 60. That's 25.981. And now we can go ahead and solve. So let's combine the negative 20 and the positive 25.981. And we get a positive 5. Let's see here. 25.981 and 25.981 plus 12 RBY equals 0. Subtract 5.981 from both sides, and I'm going to assume everyone's pretty comfortable with that at this point, so I'm not going to write it out explicitly. Subtract 5.981 from both sides. Divide both sides by 12, and RBY comes out to be negative 0.49842 kips. So again, we get a negative answer. That's telling us that our assumed direction for RBY is incorrect. And we can look at the physics of it. If we look at the free body diagram here, this 10 kip force is trying to push the beam down. That's going to load RBY. It's going to make RBY try to push up. But this 5 kip force, the vertical piece of that's trying to lift the beam up and pivot it around. And it's got a big enough arm here that it wins over the 10 kip force. So it's trying to lift the end of the beam up so much so that RBY actually has to turn around to hold the beam down. And rollers can be set up to hold the beam down. They don't always have to just push up. They can push down too, or pull down too. So this is telling us that RBY really has to be pulling down on the end of the beam, or this end of the beam is going to fly up. So RBY negative 0.49842 kips. Now we can go back to our y direction equation. And just like I mentioned with RAX, RBY came out negative. We still have to use that as negative in the equation. So we'd substitute in this value, negative 0.49842 in here. So let's simplify this down a little bit. We've got RAY. We've got minus 10. We've got negative 10. We've got positive 4.3301. And we've got a negative 0.49842. So negative 10, 4.3301. And we've got 0.49842 negative. So RAY minus 6.1683 equals 0. So we can solve that pretty easily. Add 6.1683 to both sides. And RAY equals 6.1683 kips. So there we've got our three unknowns that we were asked to find. We do have to present our final answers here. And as we get into more complex problems, it'll usually be clear how many sig figs you'd need to use. Here I've kept 5 sig figs throughout my calculation, so I'm going to round my final answers to 3 sig figs. So up here, I'm going to write a little summary box of my answers. And I'm going to include directions. Whenever you report your answers, if these values are magnitudes, RAX, RAY, and RBY are just magnitudes. The negatives and positives are telling us about directions. So what I like to do is I like to write my answers I'm going to say something like RAX is 2.5 kips. But the answer came out negative. That means that it should be to the left. So I'm going to do that. 2.5 kips to the left. That very clearly indicates what the direction is without bringing in signs, because whether negative means to the left or negative means to the right depends on the coordinate system you picked. Drawing arrows does not depend on the direction on the coordinate system. So this gives you a more universal answer, less likely to be confused. RAY was 6.1683 kips. So I'm going to round that to 3 sig figs. So that'll be 6.17. Up. And our BY, we had negative 0.49842 to 3 sig figs. That would be 0.498. Don't forget the units. And this one came out negative also, opposite the direction we drew it. So that's got to be down. So that's a perfectly fine way of writing the answers. Good idea to put in a box so that you can see it pretty easily. Another way to do it is to draw what we call a summary diagram, where you basically draw your free body diagram over again, but you draw it with the answers in the right directions. So you could say, and with everything rounded properly and labeled with units and all that. So you do 2.5 kips, 6.17 kips, and then your applied forces. So that's a summary diagram. Does the same thing, shows definitively the directions and the magnitudes of your unknowns. So that's the typical problem. Now, in most situations, we can usually guess the directions a lot more easily. You may have been expecting RAX to come out negative. You might not have been expecting RBY to come out negative. It's not always clear from the problem whether things are going to come out positive or negative. So you have to make your assumptions and let the math tell you what the right directions are. So, but this will be the foundation of pretty much every problem we solve from here on out. Any questions on this one? All right, well, it's just about that time. So let's take a break, and about 10 minutes, we'll come back. I'll run through another example, and then I'll give you one to work on your own. All right, so let's try another example. Let's take a similar setup. Most of these look pretty similar. Sometimes there's some variation on where the supports are and whether there's a roller on the left or a pin support on the left versus vice versa. Let's do one that kind of looks like a diving board. Diving board kind of free at one end, but has supports in the middle and at the other. And we'll make this this diving board. Let's make that 20 feet long. And we'll have, let's say, 16 feet to the roller support from the pin support. And we'll put, let's just put a, let's put a ton at the end of that. We'll put 2,000 pounds right at the end there. And we'll put maybe a little bit of wind blowing. We'll put 200 pounds of load blowing at it that way. And our task here is to find out what the reactions are at the supports. So find the reactions at the supports. So I'm going to call these A and B. And we can go ahead and proceed. So our first step in solving this kind of problem is first to check and see that it's in equilibrium. Well, this load pushing down at the end here, that's going to try to rotate everything around B. If you imagine this was kind of set up on a couple rollers and you stepped on the end of this beam, you'd be pretty well within reason to expect point A to come flying up. So this supported A, we should expect it's probably going to have to hold this beam down. But it's also got to fight against this 200-pound force that's trying to push everything to the left. So it's got to push to the right. The roller is going to have some force on it. It's going to be different than 200 pounds or 2,000 pounds, though, because that 2,000 pounds isn't sitting right there. There's some lever arm there. So we should expect that there's going to be perhaps more force on B due to the leverage that's happening here. So going through the problem and at least getting some idea of what the loads look like, it's good practice to help develop your intuition and to verify or at least have some idea of what your answer should look like. Can also help you to make your assumptions to minimize negative signs. So let's draw our free body diagram. So we'll draw the free body diagram of the beam. So we have 200 pounds pushing to the left there. We have the 2,000 pounds pushing down. B is a roller, and we can assume it's all sitting, unless it's otherwise drawn, you can assume it's sitting on a flat horizontal ground surface. So this is pointing up. Reaction at B in the Y direction. Then I've got my reactions at A, and from the kind of discussion of the loading here, I might anticipate that A is going to be pulling down at B. If you weren't sure at A, if you weren't sure if A was going to pull down or not, just make a guess and the math will tell you. But if you look ahead a little bit, you might reason out, I think that A is going to pull down. So I'm going to call that RAY. That's the assumption I'm making in this problem. And from the way that this side force is applied, I'd expect A to have to push to the right. So I'll call that RAX. So there's my free body diagram. Always worth pausing for a moment and making sure that you got everything. Because if you have missed a force at this point, it's a couple seconds to correct it. If you go and work the problem out and have missed and realize then you've missed a force, you've wasted a lot of time. So I want to make sure I have two applied forces. I've got those two applied forces. I've got one reaction from the roller and two reactions from the pin. So I think my setup's okay. So let's do our sums. Sum of forces in the x direction, marching left to right here. I've got RAX positive, and write my coordinate system down. To the right, positive, up is positive, and counterclockwise moments are positive. So I've got a positive RAX. Nothing from any of the other three forces except this 200 pounds to the left. So I've got minus 200. Sum of forces in the y direction. I've got RAY, but I've assumed that that's down, so it's going to go into the equation negative RAY. I've got RBY up. I've got 2,000 pounds down. The other two forces, they don't have Y components. And then I've got my sum of moments about a point, and just out of habit, I'm going to pick point A. as my pivot point. In that case, RAY and RAX, no moments because they don't push on the pivot point. RBY, that's pretty far away, so it's got an arm there, so that'll show up. That 2,000 pounds, that'll create a moment. That'll tend to make this rotate. But let's look at that 200-pound force there. Whenever the line of action of a force goes through the pivot point, it creates no moment. And the line of action of that force shoots right through A. So this is like pushing on the end of the door, trying to get it to open or close. It's not going to cause a rotation. So nothing from the 200-pound force. So only two forces with moments, RBY and the 2,000-pound force. Now, RBY happens to be 16 feet away from my pivot point. So it's got 16 for the arm and RBY for the force. Alone, RBY would produce a counterclockwise moment. So it's positive. Then we've got this 2,000 pounds 20 feet away. So we've got 20 times 2,000. That'll be 4. With 4 zeros after it, so 40,000. And that would be foot-pounds. Alone, this would provide a clockwise moment. Clockwise moments are negative. Since we're in equilibrium, or we're assuming we're in equilibrium, all of these sums have to add up to 0. And now we can go and solve our equations. Starting with the x direction equation, pretty simple to solve. Hopefully I don't have to work through the mechanics on that one. RAX is a positive 200 pounds. We can't do anything with the y direction equation because we've got too many unknowns. So we've got to jump to the moment equation. The moment equation we can work with. If we add 40,000 to both sides, we'll get 16 RBY equals 40,000. And dividing both sides by 16, RBY should come out to be, I think, 2,500, but I don't trust my mental math this late in the day. So let's see here, 40,000, 16, yep, 2,500. So notice something about RBY's answer. It came out positive, which means our assumed direction is correct. We assumed it was pushing up. The math confirmed that for us. Just like with RAX, it's positive, confirmed our assumption was correct. Well, now that we know what RBY is, we can go to the y direction equation and plug that in. So we can plug in 2,500 pounds in place of RBY. That'll give us 2,500 minus 2,000. That's a positive 500. So we'll have negative RAY plus 500 equals 0. And that should be relatively easy to solve, and I won't belabor the mechanics on it here. RAY is a positive 500. Add RAY to both sides. Easiest way to do that. So RAY is 500 pounds. That also came out positive, confirming our assumed direction. And in fact, all of our answers are exact here. We didn't do any rounding. So that's kind of nice. So let's summarize our results here. RAX came out to be 200 pounds to the right. RAY came out to be 500 pounds down. And RBY is 2,500 pounds up. So those would be our answers. So something to notice here, and this is something that's a little harder to get early on, but it definitely happens. You can easily see reactions that are higher than the applied loads. We've got geometry in play here. We've got mechanical advantage. There are all sorts of other factors that happen. So don't assume that the answers you should get should always be less than the applied loads. There's depending on the geometry of the problem, it can certainly be higher. So be aware of that. Otherwise, pretty straightforward. Any questions on this one? All right, well, let's set up a couple of them for you to try on your own. And just like the previous sessions, I'll sketch them up. I'll pause the video for a little while, and you can try and set them up, solve, ask any questions you might happen to have, or let me know if you get stuck, and we can try to work through it. And then I'll leave some time here at the end to work through the solutions. I may even put the answers up at some point here through the process, so you know what the answers are and you can check your results. So let's see here. We'll have one that looks like that. And let's see. All right, well, let's bring that up just a bit. There we go. So in both cases, find the reactions at supports A and B. All right, so here are the answers to our practicum problems in red, and we'll go ahead and work through those. So let's start with the first one. So free body diagram first. So we've got our beam. Pin supported A, we can replace with RAX and RAY. The roller support at B, RBY. Dead in the middle of the beam, we've got 5 kips. Then somewhere on the right side, we've got 3 kips. And we've got our geometry on there. All right, so there's the free body diagram coordinate system. To the right is positive, up is positive, and counterclockwise moments are positive. Let's bring that down just a bit. There we go. So there we've got our free body diagram. Let's do our sums. So sum of forces in the x direction, I've got RAX, and really nothing else has an x direction component. Sum of forces in the y direction, I've got a positive RAY. I've got a negative 5 kips, got a negative 3 kips, and a positive RBY. And then for moments, I'll pick A as my pivot point. So sum of moments about point A. RAX and RAY are out since they push on the pivot point, but everything else will have a moment. Everything else has an arm. So the 5 kip force is 5 feet away. So that's 5 times 5, 25 kip feet clockwise. So negative. The 3 kips is 8 feet away. Be careful of that. Don't mistakenly use the 3 feet here. You got to measure from your pivot point. So 8 feet times 3 kips, that's 24. Also clockwise, so negative. And then we've got RBY. RBY is 10 feet away, so 10 RBY. That one would be clockwise or counterclockwise, so positive. So there we have our sums. Because we're in equilibrium, we can set those 3 sums equal to 0, and we get our first answer right away. RAX is 0. In many of these problems, you may notice no side loads. We tend to deal mostly with gravity, weights on beams, not so much side forces. So in a lot of problems, RAX comes out to be 0. Don't try to jump too quickly at that and just automatically write down RAX is 0. Because as soon as you start doing that and getting into the habit of it, you'll get a problem that doesn't have RAX equal to 0 and things get screwed up. Let the math tell you that RAX is 0. If you see a pin support, no matter what the other forces look like, draw in 2 reactions and let the math work it out. So we've got RAX is 0. We can't do anything with the y direction, so we'll go to the moment equation. So if we simplify this down a little bit, we get negative 49 plus 10 RBY, 0. And solving that, add 49 to both sides, divide by 10. RBY will come out to be positive 4.9 kips. So our roller support is pushing up with 4.9 kips. And now that we know that, it came out positive, so we can assume, we know our assumed direction was correct. We can go back to the y direction equation and substitute in 4.9 kips for RBY. And if we run the numbers down on that, we get RAY minus 5 minus 3 is negative 8 plus 4.9 gives us a negative 3.1. And that's equal to 0. And solving that one's relatively easy. RAY is 3.1 kips. So our answers, RAX came out to be 0. RAY was 3.1 kips up. Came out positive, so our assumed direction was correct. So 3.1 kips up. And our BY was 4.9 kips, also up. Which should have been the answers I wrote down there. Now, looking at it physically, always a good idea when you've got your answers to go back and at least look at the structure and see if it makes sense. One of the easiest things to do in that regard is to look at those forces that are dead in the middle, like that 5 kip force. If it was just that 5 kip force alone, we'd expect an even split. Since it's dead in the middle, both RAX and RBX and RBY, say that again, RAY and RBY, the two Y forces should be the same. We should have 2.5 kips on both sides. The 3 kips being off center, being off to the right, is going to load up RBY more than it's going to load up RAY. If it was dead in the middle, then we'd see 4 kips on both sides because we have a total of 8 pushing down the middle. But because that 3 kips is further to the right, it's going to load RBY more and RAY less. So we get 4.9 kips on RBY, but we get 3.1 on RAY. So it makes sense that we see less load on the A support than we do on the B. So it's a good idea to go through that, and as you get more right answers and look at more of these problems, there'll be kind of a feedback process where you can look at the problem, get an idea of how the loads are going to be distributed, solve it, and then confirm that your original suspicions were correct. Any questions on the first problem? All right, and go into the second one. Second one, we have a little bit different arrangement of our supports, but still basically the same kind of problem. So let's draw out a free body diagram. So we've got our beam. Here our roller is at A, and the roller supplies one force perpendicular to the surface. So that's RAY. We've got that 10 kip force applied right on top of it. Then here in the middle of the beam, we've got our pin support. Now the pin support is going to supply 2 forces. And if I'm just kind of plowing through here and doing my free body diagram without really considering what my answers are going to look like, I'd assume these positive. If you looked ahead a little bit and thought about it, you might have made different assumptions, but I'm going to say RAY is up and RBY is to the right, or BY. There we go. Let's get the labels right. RBY and RBX. And then we've got our 2 kip force pulling up and 4 kips pulling to the right. And we've got some geometry. 2 feet and 2 feet. So there we go. There's our free body diagram coordinate system. All right, well, let's do our sums. So sum of forces in the X direction. Got nothing from over here. We've got RBX to the right. And we've got 4 kips to the right. So both of those go in positive. Take the sum of forces in the Y direction. We've got a positive RAY. We've got a negative 10 kips. We've got a positive RBY. And we've got a positive 2 kips. And then we can do our sum of moments about a point. And I guess I'll just pick A again out of support here, out of habit. That'll knock out both RAY and the 10 kip force, since those both push on the pivot point. It'll also knock out the 4 kip force, since the line of action of that force goes right through the pivot point. It'll also knock out RBX because its line of action goes through the pivot point. We assume this beam is so thin that it doesn't really matter that there might be an inch or two here in a physical beam of difference between that. It's not enough moment to matter. So the only forces that are going to have moments are going to be RBY with an arm of 2 feet and the 2 kip force with an arm of 4 feet. So we've got 2 feet and RBY. That'll be 2 RBY. Pinned there, pushing up, counterclockwise moment, so positive. And then we've got 4 and 2. That'll be 8 kip feet, also positive. Oops. And I jumped ahead here and said that's equal to 0. But that would be our sum. No other terms. Because we're in equilibrium, the sums must be 0. The x direction equation we can solve pretty quickly. RBX is negative 4 kips, which you might have anticipated if you looked at it a little more carefully and saw, well, 4 kips is pulling to the right, so something's got to pull to the left, and the only thing I've got is RBX. So RBX was 4 kips to the left. Can't do anything with y just yet, but we can go down to the moment equation. If we subtract 8 from both sides, we'll get 2RBY equals negative 8. Divide both sides by 2, and RBY is negative 4 kips. So RBY came out negative 2, and that means we assumed the wrong direction. This 2 kips is going to try to lift this whole beam up, so that pin support is going to have to hold it down. Otherwise, the thing's going to rotate, and we won't have equilibrium. So RBY must be 4 kips down. But we're stuck with the sign for working out the y direction equation. The numerical value of this symbol RBY is negative 4. So when we replace it up here, we've got to make sure we replace it with a negative 4. Don't get lost in the signs here. So now we can go ahead and finish up. RAY minus 10 minus 4 is negative 14, plus 2 is negative 12. And if we work through the solution on that one, which hopefully everyone can do pretty easily, RAY comes out to be a positive 12 kips. So that one we got right. RAY has to push up with 12 kips of force. So that would be RAY, 12 kips up. So those would be our answers there. And that should match, absent a couple scribble marks there, should match what I have there. All right, making sense there? Okay, I'll assume so. So the homework that you have for next week, homework 4, involves a number of problems similar to this. There are quite a number of problems. I think there are 5 of them on the set. The first one's pretty straightforward. It's just working with some moments. Don't find the reactions. You don't have enough information to find them. And the others are mostly problems like what we've worked on tonight, except for problem 5, which has a little bit of a challenge in it. So I expect to have some questions on problem 5 next week, but it's worth taking a look a little bit early if you found yourself maybe running out of time a little bit on this current homework assignment, the one due tonight. You might want to start a little bit earlier on number 4. Well, if there are no other questions, then have a good night, have a good weekend, and I will see you Monday evening.
Take it easy.
Thank you.